Production. So today I'm going to talk about the updates on using libfabrics in MPICH. Just a brief overview about of the talk today. So mostly I'm going to start with what is MPICH in case some of you are not familiar with it, and our adoption of using OFI and some updates to the recent version and some work in progress stuff. Okay, so MPICH is a high performance MPI implementation that we do at Argonne. So it has all the MPI features, including the latest MPI4 standard. It's open source and it's actively developed by Argonne National Lab in collaboration with many vendors around the globe. So what we usually say is MPICH is not a single library, but a broader MPICH ecosystem community. Because we have this open source MPICH library that our vendor collaborators would take our open source code and apply their special source for their hardware, and therefore they can bring optimum benefit for their users. So this model allows us many flexibility because as the MPICH team, we're able to focus on general optimization while our vendors can focus on the optimization for the target hardwares. And we also work closely with application and tools developer to make the MPICH library work well with them. So we started using libfabric in MPICH about well, actually I think it's maybe 6-7 years ago. The main reason that we used the OFI back then was for its close abstraction of MPI and be able to fully utilize the hardware potential without us to write a lot of code to adapt to the hardware. And also, one of the reasons is back then it has a full-fledged socket provider that allows us to easily prototype our code on our own laptop. So this is the overall architecture of MPICH today. So on top, we have this MPI layer, which is device-independent functionalities, including how the data type is handled and various collective algorithms. And the lower layer is where the actual communication magic happens. So currently we're using this new abstract device called CH4, which consists of several components for collectives, active message. But those are basically for the fallback functionality where the hardware support for communication is not available. For the native communication path, we're using OFI and USX on the line to move the data, and also we have a bunch of shared memory communication models for various capability, including for inter-process communication between multiple GPUs. So currently we have two series of MPICH release. One is the 3.4 series. This one is basically the one that officially adopted the CH4 device as a default. The main goal in this CH4 device was to achieve low latency and a lightweight communication, especially when there's hardware support from the network, and we're trying to use the native path as much as possible. And we're also trying to address the performance issue related to MPI monothreaded MPI communication. I'll talk. There's more about that later. And also, we added initial support for GPU, which the user can use GPU buffer for communication. And a much newer MPICH 4.0 series is released last year, and a big focus in this one is to have a comprehensive and enhanced support for GPU communication. So there's several model of communication that we're looking into there. For example, we have the native data movement between the GPU and GPU across two nodes. That's where we're utilizing the underlying hardware support from that is built into libfabric and UCX to do that. But apart from that, we also have a GPU fallback path for the cases where if there's a complex non-contiguous data type that user use, and in that case we can use a pack buffer that we allocate on GPU to pack the data before sending it over network. And also we added the GPU IPC communication in the shared memory module. So that's the overall feature of the MPICH 4.0 series. And apart from that, another major improvement is we have the full support for multi-VCI optimization for multi-threaded MPI communication. So until not until 4.0, we have the all the different parts, including point-to-point communication, RMA, and active message, be able to utilize in multiple VCIs. So the reason of having this multi-VCI is because traditionally with MPI multi-threaded communication, different thread would have to contain for the communication resource in order to do the communication, which this contention historically results in low performance in message rate and latency in comparing to the MPI thread single model. So what we did in the MPICH 4.0 series is try to utilize the multiple communication contexts that libraries like libfabric can provide. So what we end up with is we can pre-create multiple communication contexts and CQs, and at the runtime we can map the communication traffic from different communicator or based on where the target rank is, and map these traffic to these different communication contexts. So in that case, inside the MPI, we don't have to lock these on these different communication contexts if two threads are trying to do it. For example, if we have what we usually suggest user to do today is that if you're programming with multi-thread MPI communication, we would highly recommend you to create multiple communicators where essentially you have one communicator dedicated to each of the threads. So in that case, MPI internally can take these all different communicators and map them to different VCIs or lower level communication contexts. So in that case, when multiple threads are doing communication on these communicators, there's no contention among each other. Okay, so and this is what the optimization for the multi-thread MPI that we did. So one of the major work in progress item that we did from last year is what we call the GPU stream aware MPI. So in MPICH today, we can use GPU buffer for communication, but from the user perspective, this is it might not be sufficient to attain a good performance for their application. For example, actually, we got this request from the PET-C team at Argonne. They were trying to use something like this. They were trying to use GPU to do their computation, but the problem is because the MPI communication still runs on CPU, so there has to be a synchronization, explicit synchronization that the user need to do to say, oh, the GPU has finished the computation. Now I can have the CPU to do an MPI send, which there's several problems with. One is this synchronization unfortunately introduce a delay, not only delay but also idling on the GPU, because now that GPU have to wait for some of communication to go in. So there's also missed opportunity for computation and communication overlapping. But more importantly, if you you have multiple kernel launches, and if you need to synchronize the communication in between them, it's also very hard to hide the launching cost of the GPU kernels, which is also bad for performance. The idea of having a GPU stream aware MPI is basically allowing the GPU, allowing MPI to enqueue a MPI operation onto the GPU stream. So if you look at the figure on the left, this is basically how the application do communication with that involves GPU kernels, but without the GPU aware stream aware MPI. So essentially, when the CPU is doing the communication, the GPU could be idle. But of course, if you carefully manage all the computation and dependency between the kernels on multiple stream, you might be able to avoid that. But here, if there's only a single stream, this is what we have. So the GPU stream aware MPI, or the core idea is create this GPU stream triggered operation where the MPI application on the CPU can just simply prepare a ISIN operation, but not actually doing the sending the data. Instead of sending the data, it will create a small work, or what we call a trigger point, and enqueue it on the GPU stream. In that case, whenever the GPU stream finish the kernel execution, it hit this trigger point, and that trigger point will in turn trigger the actual data transfer of the ISIN, because by that time, hopefully the data that the ISIN is going to send is ready in the buffer. So in our implementation, we could use a CPU helper thread to do the actual transmission. But that, as you can see from the figure, it's we have a much better chance to overlap the communication and whatever computation that is following on the GPU stream. And of course, in this particular example, there's the requirement is that the kernel 2 is not going to touch the data that's being sent. Otherwise, it's wrong program. So there's essentially there's three things we're trying to do. We're trying to handle in this prototype. So one is how to do the triggering. So this work is actually we learn a lot from our multiple discussions with Jim Dinan from NVIDIA, since we're mostly prototyping this using NVIDIA GPU and CUDA library. We learned a lot from Jim, and so the long story short, we're basically creating two type of work item that we can enqueue on GPU stream. One is a set kernel, or a set operation. This is essentially for GPU to trigger something to happen on CPU. For example, the GPU can use this trigger to trigger an ISIN to actually transfer the data, or trigger I receive to look into the incoming messages and try to match an incoming message. And the other operation is a wait. Wait is on the other hand, it will block the stream for something until something happens on the CPU. So this is more of it will be useful for the cases where if I'm going to do MPI wait on the GPU stream, this is in our prototype, it's the MPI helper thread is gonna actually call the wait function and to pull the progress. At the same time, the GPU stream will just wait for that flag to be set and until it's done. So as we were prototyping this, we were I realized we could also do a CPU GPU like CPU GPU barrier like operation on Fury. Not sure how that's going to be useful, but it's an interesting discovery, sort of. So currently there's 3 ways that we implement these triggering function. So there's the simplest one would be the launch host function, or stream callback function if you're using a AMD's ROCm library. So this is essentially allowing the GPU stream to call host function, And in the CUDA implementation, it will be a CUDA thread that actually runs that function. And there's some caveat with this because you're not supposed to call any CUDA function inside this host function. So there's some limitation. While in our prototype, it does work if we just put the entire MPI isend in there. So it's a very simple implementation. But since there's no guaranteed behavior, so it's fairly hard to do that. But if we one simple way to do is we can just use this host function to set the flag. So like the figure on the left, and we can still have the MPICH helper thread to do the actual communication. So that would work around this CUDA function call limitation. Although because now we're dealing multiple threads, there's overhead context switching between them. But that's what's available in the NVIDIA and AMD's library. A more generalized version is to launch a GPU kernel. Simply just use a kernel to set flags. So this is more of the right hand figure model, where we have the GPU kernel on the stream to set flag, and then we have the MPI helper thread to wait for the flag to be set and then do the same. And similarly for NVIDIA's CUDA driver API, there is also a stream memory operation that is lighter weight than launching the GPU kernels, but we can achieve the same functionality. But I didn't find anything similar to that in AMD's and Intel's API documentation. So that implementation might be a little bit restrictive to only NVIDIA. And also there's also some limitations if we're trying to implement a MPI blocking operation. For example, if I'm not doing an isend but doing an MPI send and on the stream, how to make sure that that blocking operation actually meets the semantics of the blocking operation that of MPI is also there's some restriction that is hard to do with stream memo, but it's much more easy to do with GPU kernels. So that's the triggering part. The second part is actually related to the communication. So as you can see, since we're introducing this MPI helper thread, the entire MPI application, even though you may not be creating pthread or using OpenMP or something, it is essentially become a multi-threaded MPI because the helper thread is doing communication, and the timing is actually controlled by the GPU. So it's in fact multiple threads. So in the current prototype, using MPI thread multiple is required. I mean, technically, depending on how the MPI library is implemented and how the user application is written, it can work with MPI thread serialized. But basically, we're more concerned about the general case where is doing multi-thread MPI communication, and so the good thing is, since we have the multi-VCI capability already built in MPICH 4.0, we can utilize that. So just here is just a very simple example that we have a sender process and receiver process, and each of them have one GPU thread doing communication, and at the same time, the host thread is also doing communication. So if you're using VCI, we can isolate their traffic onto two different OFI contexts. So this OFI context is actually the TX and RX context and CQ and other components. So we just encapsulate it as a OFI context in the figure. So so if this is essentially creates two dedicated pipes between these two processes, so the traffic can be isolated. However, one of the challenge related to this is that how we can make sure that they get there, because these OFI contexts are local resource and only visible to the process itself. So in order to set up this agreement that the OFI context one on the sender is going to talk to the OFI context one on the receiver. There has to be some exchange to figuring that information out. So that which leads to the proposed interface that we're doing in our prototypes. So these are the major functions that we're trying to add to MPI. So there's also other smaller like MPI infos and other small things that is needed, but for the sake of the discussion, I'm just omitting them. So the core idea in here is we're introducing a concept called MPIX stream. So this is while we're using it for GPU stream, but it's not equal to a GPU stream. It can basically what it represents is a serialized context. So a serialization context, because if you think about if it's a GPU stream, anything that happens on the GPU for any communication that happens on that GPU stream is going to be serialized by default. And also this MPIX stream could also be representing a CPU thread. So we can also use this to optimize multi-threaded communication. But the core idea is having a explicit stream allows the user to tell MPI that this is a different traffic flow. So then with that, MPI internally can know for sure that this is something that we could safely and probably ideally want to always allocate a dedicated communication context for. So with that, usually if you're using GPU stream, you can create an MPIX stream and bind a GPU stream with it. There's a first brief code example in the next slide. So the second thing is what we introduced called MPIX stream com. So this is essentially you create a communicator from it creates a new communicator from existing one and tie a MPIX stream to it. So this is actually a collective operation. So what is for all the participants in this communicator to figuring out which context they should be used. Since when we create an MPIX stream, we're sort of want to we already let the MPI library knows that this is probably going to need a dedicated OFI context. So that will address the problem of context being local, but for communication to happen, everyone need to know where the target context is going to be, so communication can happen. So this is what mainly the stream concrete do. There's also a stream concrete multiplex function. This is mainly for if you have many streams that you need to use for communication, but you're not necessarily want to create so many just stream count communicators. So there's a workaround for that. And lastly, there's the operation that we're doing for that that we can enqueue on GPU. Essentially, we're currently looking at point-to-point communication, which means MPI send, MPI receive, I send, I receive, and we have this enqueue version for them. The requirement, the parameter is essentially the same as other MPI point-to-point communication, but the requirement is if you put a stream com here, it will enqueue the operation on the stream. And there's also a wait and wait out enqueue for completing the request. So this is just a very simple example. We have a sender and receiver process, and each of them creates their own CUDA stream. And then we create an MPIX stream based on the CUDA stream. And then in third step, they create a stream conf that not only identify which stream to use on each side, but also internally creates this mapping between the communication and the OFI context. And then after that, they can just do MPIX and enqueue to put an operation on the stream, and also do MPI wait enqueue to block the stream until that ISIN is completed. and in between this, the user is free to do other things. And so at the end of it, the user may just do a big synchronize and just make sure everything is finished. Okay, so that's the code example. So next step about this is, since we've been working on this prototype for quite a while, and we are planning to put this into the MPICH 4.1 releases. The alpha one should be coming out in a couple of weeks. So first of all, this is under MPIX namespace. It's non-standard, and it's also optional for the users of the library or for our collaborators. You can disable it completely. The main goal of we're trying to push this is one reason is we really want to engage with our users and vendors to see how they want to use the MPI stream-aware MPI, and also trying to identify what is the better way to create the API, because we also have internal discussion whether this stream com is really needed, or maybe it's too restrictive in one way. Maybe just adding the stream parameters into each of the MPI function might be a better, a more flexible model. Although we're creating a lot more new functions that the user needs to learn. So the API is mostly going to change in the future, depending on how this is going to go, how this proposal is may or may not be adopted by the hybrid program model or group of the MPI forum. And also, and apart from that, we also in our prototype we look into expanding support to other GPU vendors. Right now we're doing a prototype with NVIDIA, but the next one we're trying to do is with Intel GPUs. And also further down, since right now we're just the prototype essentially the triggered operation is just doing MPI ISIN. But we're also looking at other opportunities and maybe optimization that can be used, maybe using a OFI triggered operation or something that we can essentially having more and more work being prepared when you enqueue the operation and making the actual triggering part as small as possible. So that's the overall direction that we're working on. So with that, I think this is pretty much all I want to talk about in this talk. Thanks everyone, and I'm happy to take any questions.
Okay, thank you very much. We did have a question.
Yeah.
What does MPICOM compare return if you pass handles to two multiplex communicators derived from the same streamcom? Would we need to add a comparison result in between the MPI ident and the MPI congruent? Sorry, forgive me.
Well, that's a very specific question. The quick answer is we haven't thought about that. Actually, I have to admit that this proposed interface is there's many details. For example, since we're doing streamcom and if you use streamcom for the communication, and it will implicitly means that this operation is going to encode on this particular GPU stream that in the streamcom. Then the problem with is that if I do an MPI wait enqueue, right? Because the wait function signature doesn't take any communicator, it takes a request. So then there's a two level of indirect reasoning that the user have to do, because then the user will take this request and it will need to figure out the request is coming from a MPI send or receive enqueue operation which uses streamcom. So and that will makes this wait operation enqueue on that particular stream. So it's also not I mean could be complex for user to understand. which is why we have some internal discussion about whether this is a correct interface. And it's also why that we want to put this out to the user and letting user try and see what kind of model works best for them. Yeah. So yeah, I see. Is Jim asking that question? I think I'm happy. I'm happy to have more discussion. There's a lot of multiple can of worms with this that I opened with this extension proposal.
Very good. Are there any other questions, or Jim, did you have a follow-up question? Okay, I see no follow-up questions. I see no other questions in the queue. Oh, okay, good. Oh, I guess we do have one. Some libfabric providers FI HMEM capabilities require memory descriptors, while MPI standard does not require MPICH. I think maybe we didn't get the whole question.
Well, let me let me see how I'm gonna.
Do MPICH require does MPICH do memory registration on GPU memory? There we are. Okay.
GPU memory. Yeah, I think we do that today. I probably need to double check the actual code. I think we're using the FI HMM capabilities today.
Does that answer your question? Right? Is there a
GPU memory cache?
cache?
I don't. I'm not sure what do you mean by GPU memory cache.
In MPICH.
Yeah, as for its functionality, I don't think we have anything like that. GPU memory registration cache. Yes, we do have that for the GPU IPC communication. Yes, we internally maintains a AVL tree for all the memory space that we registered, so that we can. It's mainly a optimization for the GPU IPC operation, because depending on the communication and where the which device the memory is mapped to, there's performance difference between a GPU read and write from different devices. Yes, we have a cache for that.
Can you throw up the GitHub link again on the slide?
Oh yeah, sure. You mean the this one? This
yeah, thanks. Appreciate it.
Yeah. The link here is just so you'll get a full description of what the APIs that we're envisioning in this, and also if you have any suggestion you like it or don't like it, we're happy to take suggestions and discussions, and if we can revise this version and put out one that people are more inclined to use, we're happy to do that. Yes.
Very good. Thank you. Okay, thank you very much for the presentation.
Thank you.